to stop your talking time. I believe we are missing the first speaker. So Seblu, if you're there, can you make yourself known? Yeah, I think we are missing the first speaker. Okay. In which case, we're going to move the whole program forward, up a little bit. So Grace, you're going to go first. And then if Seblu comes online at the end, then they can speak. Okay, so we're going to start in about another minute or so. I'm just going to check if everybody's in. Okay. Okay, thanks very much, everyone. We're going to be starting the next session. Unfortunately, our first speaker is not available, so we're going to skip straight to our second speaker, Grace Katumi. And she's going to be telling us about new ideas from old friends. So please take it away, Grace. I'll give you a warning after 10 minutes.
Thank you. So, are you able to hear me and see my screen?
Yes.
Okay, thank you. So, let me first take this opportunity to thank the organizers of this conference and for organizing this conference and for giving me the opportunity to present what we are working on. So I'm Grace from Barra University of Science and Technology. Currently, I'm a master's student. And the work I'm presenting here, I'm working with a couple of collaborators led by Professor Markov, where we are trying to understand the jet emission of stellar mass black holes. And that's how we come up to revisit these two in particular, J1118 and J1550. So we find that all dark holes accrete matter, and then this accretion process is the most efficient process in the universe. And thus, for supermassive black holes, which are accreting, they play a great role in the cosmic evolution. One way in which they affect the environment is by depositing energy through the outflows they launch. But then in these supermassive black holes, we are not able to see how these outflows are connected to the inflowing matter because these systems evolve too slowly. So we are not able to see that. But then luckily enough, we are able to see this. We are able to see this in stellar mass black holes or the X-ray binaries. So we find the X-ray binaries being excellent laboratories for studying accretion physics, thus allowing us to probe the connection between outflows and inflows, because for the X-ray binaries, they evolve on human time scales. And the outflows we are talking about in this project, they are the jets, where we see these jets emitting in radio emission, but then their spectrum can extend up to higher energies. So it is supposed that radio light is at low energies. The electrons are moving very fast at the speed of light. And then there is strong magnetic field. So this strong magnetic field causes these electrons to spiral around it, and thus forming sort of a helix. And that's how we come up with radio emission, or what we can call the synchrotron radiation. And if we have, of course, we are having very many electrons which are moving at the speed of light. There is strong magnetic field. So if an electron is moving at the speed of light, it will form or it will produce a spectrum like the hump that we are seeing in this diagram. And now that we are having very many of them that are gyrating along the magnetic field, each of them will produce its own spectrum. And once we add up all the contribution from all these electrons, then we come up with what we call a power law spectrum. And now this background, let's explore more about the project. So in this project, we are aiming at differentiating synchrotron and compton and inverse compton origins of X-ray emission in peculiar epochs using refraction, which is a proxy that Sarah came up with in 2004 to differentiate these two radiative mechanisms. So if we are having X-ray photons hitting the disk, they will be reprocessed into peculiar signatures. That is the iron 9 at 6 D, and then a compton hump around 10 to 30 keV. For inverse compton scattering, it is likely to be produced from the base of the jet, or what we can call the corona. And thus many photons will hit the disk, producing an X-ray spectrum, which is dominated by refraction. Vice versa, the non-thermal synchrotron emission is likely to come from regions far away from the black holes. So we find that most of the photons here, they are beamed away from the disk. And in this case, we are likely to come up with low refraction fraction values. And here we are defining these refraction fraction values as the ratio between the reflected photons and to the non-reflected photons. So if we have higher refraction fraction values, that means that we have inverse Compton dominating and the X-ray spectrum is being dominated by refraction. But if we have low values of refraction fraction, it means it is synchrotron emission dominating and the emission is far away from the black hole. And to understand these radiative mechanisms, multi-wavelength data is needed. And this is how we started by combining the rosy X-ray timing explorer data of the outbursts of J1118 and J1550 from 2000 and 2005. And then we considered the observations in hard state where we don't find refraction in the X-ray spectra by using what we call the phenomenological models. And then we continued with the fitting of this data. And for spectral fitting, we are using an improved model, which is the synchrotron plus inverse Compton jet model. And here we are calling it the BHJET model. And we find this model being better because if we look at the previous models that have been used, they only consider the contribution from the corona or the thermal disk emission and ignore the jet contribution, even though or yet we see the jet being an integral part of the X-ray binaries and their systems. So this is the model we are using here is a multi-wavelength steady state corona plus inverse plus jet model. The idea about this model is that we are trying to compare the inner regions at the base of the jet, which emit in X-rays. We are comparing them with the outer regions, which are emitting in infrared or radio. And then after we combine all the regions to come up with a compact jet. So thermoparticles are injected at the base of the jet. That means we should.
Grace, can you hear us? Grace? Oh. Yeah, good idea. So, Grace, if you can hear me, can you just raise your hand on Zoom? Oh, wait, there we go.
And
I
Steve
think
in. Okay.
you froze for a minute or two. Um, can
Yes.
can you hear me now?
Yes, I can get you.
Okay,
Can I get back briefly?
please, yeah, just go back one slide and carry on what you
Okay.
were saying.
Okay, thank you. So here I was trying to explain
Thank
the
you.
model that we to hear me now.
Yes, you sound
Okay.
fine now. Go ahead.
Okay. So here I was trying to explain the model that we are using, and I was saying that we are using a synchrotron plus inverse compton jet model, the one that we are calling BHJET in this project. And it is a better model compared to the previous models, because we see for the previous ones, they would consider contribution from the thermal emission and then corona emission.
Grace, if you can hear me, we've lost you again.
Regions which emit in the X-rays with the outer regions which emit in infrared or radio. So thermoparticles are injected at the base of the jet. Then at some point they are accelerated into a paddle. We come up with the paddle spectrum. And that's how we combine the other regions to come up with a full compact jet. And so using this model, we have managed to obtain these fits. We are showing the fits obtained from data of 2005 outburst of J1118. I have considered the data of high luminosity and that one with low luminosity. So on y-axis, we have intensity in mid-junk sky. And then on x-axis, we have frequency in hertz. For the green line, it shows us the non-thermal synchrotron, which becomes optically thin at higher frequencies and extends to X-rays. But then at low frequencies, it produces a flat radio spectrum and it is optically thick. Then for the cyan bump, that one shows us the non-thermal synchrotron emission at the base of the jet. For the purple one, that is for the directed photons of the disk. And then for the blue, they indicate inverse Compton, where photons are being scattered off the disk. And so here we have the reduced chi-squares. Someone may wonder why they are not close to 1, but this is due to uncertainties which come from different telescopes, because we obtain data from different telescopes in different bands. So it is hard to attain the
Grace, you've
reduced
got 2 minutes
chi-square.
left. Thanks.
Okay, thank you. So it's hard to achieve that reduced chi-square of 1. And then for the fits of 2000 outburst, at first we considered data without UV. Then because for UV, it was hard to obtain it, but then recently we were able to obtain it using the extreme ultraviolet explorer. I have to say honestly that this is not the best fit for this, because we obtained data not in time, but then I wanted to show it here at the conference. So this is really not the best fit, but I'm working on it. And then we have to zoom in to check whether we have low reflection fraction values in the X-ray band. Still, this is intensity in mid-junk sky and then energy in KeV. But then we see that the reflection fraction values that we are obtaining here are low, and we are referring them to a standard value that Sarah came up with in 2004. That is a value which is 0.1 in her paper. So when we compare with our values that we have obtained here, they are really low. And then for the one without UV, it is still low. This one I've said I'm still working on it, but I'm expecting also the values to be really low. And so based on the results that we have so far, we are seeing that jets may contribute to the emission process. And the data in J1118 is likely to be jet dominated since it shows low refraction fraction. And as a pilot study with J1118, we still have a lot to understand. So we have to look at more other sources, like how I'm to look at J1550 next. So with that, thank you so much for listening.
Thank you so much, Grace. Very well done on the talk, despite the slight technical hitches. Does anyone in the room have any questions? Yes, there's one at the back. Just want to check.
Hi there. Thanks, Grace, for a great talk. I just wanted to ask, is reflection the only way that the disk can radiate in X-rays, or have you included sort of intrinsic emission from the disk, like black body emission?
Oh, yeah. Can you rephrase your question? Paraphrase, maybe, if I may say. Sorry.
Okay. I was just wondering if the so you're assuming that the X-rays from the disk are all from reflection, or could some of the X-rays from the disk be from just black body emission from the disk itself?
It's not the only way that, it's not only refraction that X-rays are produced, because X-rays can be produced in two ways, either via synchrotron self-compton or inverse compton. So here I can say that is not the only way these X-ray emission can be produced in more than one way.
Okay, thanks, Grace. Vanessa says you answered the question. Any other questions in the room? Any on Zoom? If you have a question on Zoom, you can just raise your hand. Just keeping an eye on the list. Oh, there's a question here in the room. Go ahead.
Yeah, please, I want to ask if there was any real-time observation.
The question was, were there any real-time observations? Is that right?
Yes.
Sorry, come again?
Did you do any real-time observation, or you simulated the results?
I just did the modeling. We are modeling the data that, because we are considering data that was taken at the same time, on the same day from all the bands. So after getting all this data, what I did, it was to do the modeling using this improved model.
Okay, that's fine.
Yeah. Yeah.
Okay. Any final questions? Okay. Thank you so much for a great talk, Grace. We'll move on to our next speaker. Let's thank Grace again.
Okay, thank you.
Okay, our next speaker is Brian van Solen. Brian, do you want to share your screen?
Yeah, just trying to find it. Good. This one. All right, there we go.
That looks great. Thank you. Go ahead.
Okay, great. So I guess the other speaker's not here, so I have like half an hour to talk. So I'll be talking today on work we've been doing with SALT and the consequences of that, which is looking at updated binary solution for 1FGL J1018.6/5856, which will just be 1FGL from now on, which is a gamma ray binary system. So unlike the systems that the X-ray binary systems that were just spoken about by Grace in the previous talk, gamma ray binaries are a very rare class of binary system that are producing most of their energy in a new UFO distribution at the gamma ray regime. They're extremely rare. Like I said, we have less than 10 of them, and here is just as an illustration the full Fermi light, so Fermi all sky image where you can actually see some of these systems popping out. We have one detected all the way to the LMC. And so the big question we have of these systems is, how exactly are they producing the gamma rays? Why are these few handful of systems able to produce emission all the way up to TeV energies, whereas X-ray binaries typically only produce energies up to so-called peak at X-ray regimes? And there's two competing ideas. So just starting on the right is the idea that, well, we do have a micro-quasar accretion type scenario where we have an accretion disk and a jet, and the jet is producing emission. And for whatever reason, even the jet is more powerful, or we happen to have a more favorable line of sight, sort of like micro-quasar type, micro-blazar type scenario, we see enhanced gamma ray emission in systems. The difficulty with this is that, at least up to this stage, for a lot of the systems, the emission is varies with orbit, but it's consistent from orbit to orbit. We don't see the sort of hard to soft changes that we typically see with X-ray binaries. The other idea is, which is the one on the left, is that these systems contain a young pulsar. So basically we have a non-accreting young pulsar that prevents the accretion, and we produce a shock front. And that shock front is the result of the pulsar wind basically slamming into the stellar wind. We get particle acceleration in that regime, or that region rather, and this is what's producing then the gamma ray emission. We're pretty certain this is occurring in one of them. There's a non-accreting pulsar system, PSPR 1259-63, and one other long-term system where we can detect the pulsations. Unfortunately, for the rest of the binaries, we can't detect a pulse signal, but they all have smaller orbital periods, and this means that any pulse signal is probably being lost within the, is being absorbed by the stellar wind. Of course, the advantage of this is it also explains why we have so few of them, because what it means is that the gamma ray binary phase is then just a very short time in the evolution of a binary system, that after the one star goes supernova and it forms a pulsar, there's a short period where the pulsar is spinning fast enough to prevent accretion, and that will then slow down, and once accretion starts, we switch from a gamma ray binary to an X-ray binary. So the idea is not quite exactly the same, but it's the analogy to something like the Crab pulsar. We hear the pulsar in the center is powering all the emission and powering the nebula, but we're taking this and we're compacting it into a binary system. And someone once told me never put just a table up on a slide, but I did it anyway, just to illustrate the nice thing about studying all of these sources. You can get them all on one slide. You know them all by name, right? And they are varying here from about a 4-day period up to about a 50-year period. All of them, except 1 or 2, have been detected at GeV and TeV emission. They all have O or BE type star companions. And the one I'll be talking about today is 1FGL. So this was discovered in 2012 by the Fermi-LAC collaboration as a variable about 16.6 day period in the Fermi-LAC data. It's subsequently been observed by Hess and other telescopes, and you can see here the phase folded light curve. And so what we see is very typical for gamma ray binaries in GeV, right? We have a peak here at phase 1. Phase 1 in this case is defined by the peak in the Fermi light curve. We see a similar light curve at GeV energies, though there's a slight, they're not exactly in phase with each other, and this is also very typical for what we see. At sort of low energy GeV, it's sort of a stable emission. And then interesting, at X-ray observations, we get a spike here at the same, roughly the same phase as the GeV emission. But we get a secondary feature over here at about phase 0.3 to phase 0.4, which is more difficult to explain. Why are we getting a double feature here? And from observations from 2012 to 2013, there's also a hint that there's variation. You can see if you follow the green points, it peaks here nicely, but the blue points have a minimum there. The red points show some scatter. And so part of trying to understand the system is to get a better understanding of the binary solution to try and model this. Back in 2015, Anne et al. Got the best orbital period so far of about 16.554 days. And in 2017, they proposed a model for how to get this, right? The binary system is proposed to look like this. And so what we're seeing is the spike in gamma rays and X-rays here at about phase 0. So this is an inferior conjunction. So the proposal is we have a pulsar wind nebula system, but what's happening is the material is flowing away from the pulsar, and it ends up having a bulk Lorentz factor, and so we get a Doppler boosting effect. So effectively, as we're looking down that outflow, we see a very fast increase in the emission. and it then proposed that the increase in the X-ray would be up here at about periastron, and so that you're either getting a closer shock front, so the X-ray is turning on, or you're getting more interaction between the star and the pulsar. And that works great, except it is totally contradicted by observations. So in the same year, Itu and collaborators, Itu Monacheng, took observations with SALT, and I've replotted their orbital solution just to have the same orientation here. And effectively, the solution is the inverse of what the models are suggesting, right? You still get phase 0 around about here, but the phase 4, where we're seeing the secondary enhanced X-ray emission, is now near apastron, which is a far more difficult thing to try and explain. And so this got us interested in going back and having another look at it. To get this binary solution, they needed to combine SALT data with previous archival data. And so we thought it was worth, given this discrepancy between the models and the observations, to try and refine the orbit using just SALT observations. So this is the work in preparation I present. So we observed with SALT 24 times between 2018 and 2020, with the 16-day period, just trying, it's sometimes difficult to fill in all the orbital phases. And so you can see the typical, this is the average spectrum we've received. And so we measured the radial velocity through cross correlation over about 4,500 to 5,500 Armstrongs, where we have helium and Balmer lines, cross correlating against the temperature that's created from the observations. And over here, we can see how our results compare to the previous results. The blue points are now the SALT observations, and the blue line is the fit just to the SALT observations. And you can compare that to what was previously published. So it looks just from that there's a bit of a shift in the minimum. The minimum is a bit higher, a bit smaller, which suggests a slightly more eccentric system. But the error bars are a bit big here, right? We're kind of like on a 2 sigma difference anyway. If we just split the data, we get a slightly longer orbital period, about 16.55 days. And so you already get the solution. The next question is, what is the actual orbital period? Can we refine it? And the reason we're so interested in that is that actually changes the longitude of periastron quite a bit. It changes the phase position, phase 0 position relative to periastron. And to understand the multi-wavelength behavior, we need to understand that very well. So we went down a rabbit hole of trying to independently measure the period again using Fermi-Lat. So we searched through roughly 12 years of Fermi-Lat data by doing aperture photometry in a 1 degree radius around the target. So this is all binned into 60 seconds. And then we search for a period with Lomscargel, a chi-square test, and an autocorrelation test. In each case, you can see here's the orbital period detected quite nicely. There's a harmonics also getting picked up there. There's also, this is a windowing feature. The autocorrelation is a lot noisier as expected, but the signal is actually there. So just in detail, for the Lomscargel analysis, we actually went through and checked at different energy levels what the period was. And also, because Lomscargel is assuming a sinusoidal variation, we also included higher order Fourier terms. And the black line here is the previous published period, and the red line is our new best period from using 10 terms in the Lomscargel analysis. And you can see for almost all cases, it peaks slightly longer period, slightly smaller frequency. And so our best result there is a period of about 16.5507 days with a slightly smaller error. To check that, we also then went and did a chi-squared analysis. So we just zoomed in on that frequency range. It peaks at exactly the same point using a 10 to the minus 5 day steps, 16.5507 days. The likelihood analysis, a lot noisier, right? Because of course we're trying to fold our data and then fit a model to it. And then compare that to the individual observations, which are quite low.
Brian, you've got 2 minutes left.
Right? Quite low signal to noise, right? But of course we can get we do get a peak around there, slightly higher frequency period as well. As a final check, we then just went and took our Fermi-Lat data and split this up into 3 equal components or 3 equal time gaps and folded them on the previous results, the results from the radial velocity and the results we get from the Fermi-Lat analysis. And you can hopefully see that it's far more consistent over the full 12 years using the slightly longer orbital period. So we have our orbital period. So we went and refitted our data. And so here's our binary solution. I'll skip over looking at the table again, right? And so we've gone from a model result to the previous SALT results to what we now have from just the SALT observations. So the question is, what does this actually mean in terms of how we explain the multi-wavelength and the gamma ray emission? So excuse the sort of bad sketching on PowerPoint. Roughly the peak is occurring somewhere over here. You can see inferior conjunctions at about phase 0.03. There's phase 0. And so this roughly corresponds to this phase here, where we're getting the increase in the TV, GV, and X-ray emission. And so there's a couple of different ways we could explain this, right? We're getting a higher photon field. We're closer to we're closer to the star, so inverse Compton should increase. We could also be seeing Doppler boosting effects, as was proposed, because inferior junction would still be this direction. So we're still seeing boosting towards us. The offset between the Hess TV and the GV with Fermi would also then possibly be because of like gamma-gamma absorption, that the very high energy photons are being absorbed, and we're seeing them slightly earlier before we get into the photon. The more difficult thing to explain is why are we getting the secondary increase here in the green region, right, at X-rays. So do we have a pulsar wind versus accretion? And these are just sort of ideas we're still throwing around. Is there an accretion system and there's some sort of buildup of material and the X-rays peak a bit later? Is there a super orbital period in the data that we haven't detected and that there's variation over a longer term timescale, which is being seen over here? We haven't seen evidence for that in the Fermi-like curves, but this has been seen for some other systems. Is this a different electron population? Is it not the main population of electrons that are producing it? The radio peaks at about the same phase. And so maybe we're just seeing electrons cooling off, and in some cases they're producing more X-rays. The other thing is we've gone back and had a look at this quickly, reanalyze the archival X-ray data. So if you compare the dark blue to the light blue, if you can tune your eye into that with Swift data, in the blue you can see, well, there's definitely a double peak, but this is requiring a fixed slope. If the slope is freer, then that becomes a lot more problematic. Your error bars get a lot higher, though of course Chandra is also showing a high state here. So then it becomes, well, is it a question of that it's just the signal to noise in the X-rays not high enough and we're getting an artifact that's not actually there in the light curves? So in conclusion, we have new observations and, you know, on the face, it's just slightly different orientations, but it means we have to reinterpret the multi-wavelength behavior from the system. The peaks in the X-ray and the gamma ray near phase 0, yeah, we can explain that. The smaller peak around X-ray, that's more difficult. And so now we have to ask more questions, and that's great because that means we can do more science. And so we need to look for more X-ray observations. And I can see the chair is standing very closely by the podium. So I'll stop there and thank you very much.
Great, thank you so much, Brian. Unfortunately, we've gained a little bit of extra time by missing a speaker, so we do have some time for questions. Any questions from the room? Nothing. Oh, there's one at the back. Vanessa?
Hi, Brian. Thank you. It's Vanessa here.
Hi, Vanessa.
I just wanted to ask, did you say you didn't have enough statistics to look at the X-ray spectra at different phases?
So we just went back, as my colleagues has done the X-ray analysis, we went back and he reanalyzed the X-ray data, and from the Swift stuff, he says there's not enough statistics to look at the index, and that if you do the analysis with holding the index versus keeping it free, you get a slightly different behavior we get this different behavior in the light curve, and that region where you have a secondary bump basically becomes noise. And so when we're still debating this, does this now mean that this is just an artifact of a low signal to noise, or is it actually there with is that secondary feature there? And so we're looking at, we probably need to get newer X-ray observations with different telescopes to improve the signal to noise.
Okay, thanks.
Any other questions? Yeah, there's one here, David.
Hi, Brian. I was wondering about the radio properties of these gamma ray binaries. What is known, what is not known? In particular, whether Meerkat is as a potential tool for their study?
So it's varying from system to system. We know they are all, well, most of them are bright. We have radio detections from most of them. We have a radio detection from this one as well. The assumption that's sort of often made is that the radio emission is probably coming from a more extended region. And so whatever electrons are being producing, the X-ray and the TeV close to the binary, as they're cooling, they're then producing the radio emission, which may be why the radio is very often then out of phase with the others. There have been radio studies that have shown that there are extended radio emission around a couple of these binary systems. If you want to talk about meerkat observations, you're in the room, chat with Vanessa, and I don't know if Ita is there as well, because I know there's stuff being done there as well with like meerkat where we can try and look at this. One of the systems we looked at last year, 1259, that also shows sort of variable radio emission, which is much more in phase with the multi-wavelength. So these are also systems that are interested to look at the radio. Typically, it's assumed it's probably further out, and so it's a bit more difficult to link to the binary, well, to model with the binary.
Cool. Okay. Any other questions? Anything from on Zoom? I don't see any hands or anything in the chat. Brian, your talk was just crystal clear.
As always.
Okay, if there's nothing else, then let's thank Brian again for a great talk. And our last talk for this session is Christo Fenter, who's going to be talking about an African contribution to global pulsar science. Thanks, Christo.
Thank you. Let me share my screen. So yeah, it's a slightly ambitious title. I'm going to try and fit in as much as possible.
Oh, there we go. There we go. We can see and hear you perfectly. Thank you. Go ahead.
Wonderful. Thanks. Yeah, slightly ambitious title, and I have to haste to say that this is not possible without international collaboration, and I've listed quite a few names there. Over the years, we've had great support from in-country and outside of the country researchers, also interested in this wonderful phenomenon of pulsar science. So I'm just going to try and fit a few of our latest topics in this talk. Our group has been involved in quite a few different topics related to pulsar science. And just to start up with a cartoon, there you see a pulsar. It's not a photograph, unfortunately. We cannot go and see how a pulsar works, but we can try and probe this with models and observations. And so you have your magnetic field structure, which is also a big question of exactly what it looks like. Is it just dipolar? Probably not. And you have pulsed emission, you have a wind of particles coming out of the pulsar magnetosphere, and you have interaction with, let's say if it's still a young pulsar, this is surrounded by a termination shock of the supernova remnant. So I'm going to split my talk into three main topics. The bulk will be pulsars, dealing with magnetospheres, light wave modeling, spectral modeling. I'll touch on pulsar nebulae. We now have the chance of doing spatiospectral modeling, since the data is getting better all the time, data are better. And then the pulsar binaries called spider binaries, I'll just mention those lastly as a final topic. So pulsars, we've been involved for many years in pulsar science and pulsar modeling. The first example I'd like to bring is from Bertie Seifert's work. So if you just look at the radio rotating vector model, it's this expression over here, and from this I will not go into all the symbols and stuff, but it's an inclination angle, observer angle, and there's the phase, and there's the polarization vector angle. And so you can infer certain things just by looking at the radio. This is the bottom panel over here, but at the top, if you add the gamma rays, then you can probably learn more. And we've been using quite a few years back, just some geometrical models to try and constrain the geometry. And this is collectively the alpha and the zeta of the pulsar, inclination and the observer angle. And there you can just see on this left bottom plot that if you just have radio only, you have this banana slice. And if you add your gamma rays, the red and the blue, you can really constrain your alpha much better. And beta is also quite constrained. And if you use both these sets, then you actually get some intersections that sometimes work and sometimes do not work out, pointing to model refinement, which is fine because that's what we are about, is to refine the models. This is a very dense plot. It comes from Bertie's PhD thesis, which recently he passed. And so I'll just try and guide you quickly. So there's an old and a new test statistic that we are using. The old one is chi-squared, and the new one is what he calls SFN, standardized. I have to remember now what is SFN, normalized flux statistic. So if you just go back one slide and see, this is what we're trying to fit the radio and the gamma ray contribution. And it's quite difficult to find the weighting for each of these, because what is the weighting? The error bars are very discrepant. There's huge error bars in the gamma and small ones in the radio. So that gives you a dominance in the radio. So at the top, just look at the colors. And the bottom, the X, is basically telling you if the gamma ray or the radio errors are dominating, smallest or largest. So you start from small to large gamma ray errors, and then from bottom to top, you have the gamma ray band contributing more or less. So in this top plot, for example, you see an overdensity of color here, and that makes sense because the gamma ray errors by hand was made to be small. And so you have a higher contribution of gamma rays where it's balanced, it's okay. But if you have a radio at the top, errors being so small, then you have a radio dominance. And with this test statistic, he was able to show that you can actually balance, look at all the colors nicely balanced all over the plot. So there's no dominance in the way that he measured this. So there's a lot of info here, and please read and refer to the upcoming papers if you have more questions. But the question is, does this work? So there's in the paper we made a contribution. The blue is when you fit the gamma ray only, and you get kind of funny radio light curves. And if you do the radio only, you get very funny gamma ray light curves. So that is in the old case when you just use chi-squared blindly. But in his case, you get some kind of nice compromise where you get a slightly less good fit for the gamma rays, but then the radio is also quite okay. So it seems to be working. We're still testing and publishing this, but we are quite excited about the prospects of applying this to future data sets. Now, moving on to gamma rays, the GeV band and the Vela pulsar, we see lovely light curves from Fermi. And also, if you split this into energy bands, you can see that the first peak disappears relative to the second one with energy. We call this the P1 over P2 effect. And you can also see some nicely measured spectra by both Fermi and Hess. And the question is, can we model this? So this is another PhD student of mine, ex-PhD. She's now a doctor. So we've been modeling this, and you can see there's a lot of details. Again, you can refer to the paper, but we do get the P1 over P2 effect. That's quite nice. We do get that the widths are becoming slightly smaller as energy goes up, and the phases, the peaks kind of remain at the same phase. So all of these things we see in the data. So we are quite happy that we can, to some extent, reproduce this in the models. And the spectra as well, we have phase average spectra that we can fit. Not a perfect fit, but it's quite okay. And then even the phase resolved spectra. So for peak 1 in the blue, you see a smaller cutoff than for peak 2. And this explains phenomenologically why this first peak disappears, because the spectrum of the first peak just cuts off earlier. But the question remains, why physically is this happening? And so we've looked at the models, and if you have radiation reaction limits, then you expect that your cutoff goes like gamma to the third over, well, this is a general expression, gamma to the third over rho, but you can have some expression for your E field if you have a certain limit. But in any case, there's a condition that tells you that the cutoff goes like, I will show in the next slide, rho to the 1/2. That means if you expect that your cutoff for the second peak should be actually associated with higher curvature radii. And that's what we see in our code. And this is a zoom in with different energy bands. And what you should look at is the colors and the tail of the distribution of rho. And it is indeed larger. You probe larger rho values, which is the particle curvature radius, the trajectory radius. particle trajectory curvature radius for peak 2 than for peak 1. So that was what we hypothesized and what we also found. So we were quite happy about that. And then moving on from GV to the TeV band, we are waiting for the Hess paper to come out in Science on this topic. There's some interesting stuff happening here, but we're still waiting. But we've seen with Hess some up to 7 TeV pulsed photons from Vela, which is very incredible. There's only a handful of pulsars seen from the ground at these TeV energies, including the Crab, and Kaminga has hundreds of GeV, and there's also 1607 or 1706 rather. And so the question is, can we model this? So in collaboration with Alice Harding, we've published a paper, and you can see she has a very nice broadband model going from the optical X-rays, GVs up until the TeV, and fitting data reasonably well. And we're starting to see also interesting effects with the P1 over P2 effect continuing into the TeV band. So that is quite interesting. And again, there's lots of details there in the paper. Please ask me afterwards or refer to the paper. And she also found the same thing we found previously, that the second peak remains in the GV band, and we see this higher systematic row in the second peak. This is now not light curves, but row actually versus phase. And you can see that she found the same in this paper. Moving on to another project. So working with Isabel Grenier and past students. So they've done some morphological fitting to light curves, cutting up these things into slices and making spectra. So this is phase averaged spectra and phase resolved spectra, and looking for trends. And this was done for 2PC, the second pulsar catalog, which included 117 gamma ray pulsars. We're now getting up to publish this third pulsar catalog, the Fermi collaboration is, and that will include about, I think, 270 pulsars, definitely more than 250. And so are there some trends? So they found, using 2PC data, some interesting trends. For example, if you just look at
Christopher, you got 2
apex.
minutes left.
Oh, okay. That's I'll skip a few slides then. That's the apex energy over there. And if you look at that versus E dot, you do see this quadratic type of trend, and also a trend with gamma. And that can be explained theoretically, and we want to reproduce this now with 3PC. Let's see if we can do a bit of PWN stuff. So there's some trends also seen by Hess, for example. They've spent some 3,000 hours of data on this. And there's many trends, but I just highlighted one over here with the model kind of explaining, but still with broad scatter what's happening over there. And we've done our own simulations with using case 75. We do spectral stuff, we do surface brightness profiles, X-ray index versus time, and also the expansion rate, and we do find reasonable results in our models. Let me highlight two more things. NICER is a little telescope sitting on the ISS, and it's probing millisecond pulsar geometries using multi-wavelength light curve modeling. That there's X-rays, there's gamma rays, and you can actually isolate the hotspots on the surface of the star. And Anu has been doing some work, my postdoc, on multipolar structures, and you can see she's moving from dipole into quadrupole and hexapole. There's the equatorial plane cut, and she hopes to apply this new field structure to this type of light curve fitting to try and constrain the magnetosphere of MSPs. She's also looking at the shape of the curvature radiation spectrum, looking at different model parameters to see if we can tweak this a little bit and learn something about electrodynamics. Let me give a shout to Louis, shout out. He's looking at AR-SCO, which is a wide Wolf pulsar-like system. And David Buckley and company, Steve Potter, have been looking at this very interesting system, Pete Meintjes, and doing some really great work with the polarization properties in the optical. So he's been modeling this, solving from first principles the Lorentz equation, using different initial conditions for Lorentz factors, pitch angles, and he's finding from first principles a magnetic mirror. You can see here you inject particles, they come in, and they turn around at some termination distance, at the mirror distance, and then they move out again, but every time losing some energy. And this is for different super-relativistic and general assumptions. So there's an upcoming paper on this. And then lastly, the spiders. Let me move to our results. I think on this one, we've been modeling. If you just look at the nice picture again, there's a pulsar, there's a companion, there's some kind of, not really accretion disk, but inflow and the shock set up. And then you can model the light curves you think will come out of this and the spectra. And we are seeing that we are hopeful that HAZE will see some of this, or CTA at least in future will probe this. So I'll just stop with the conclusions then, saying that there's various contributions that our group has made, but I have to emphasize the very strong international collaboration and also local national collaboration that is important. And there's also a very interesting interplay of theory and observations. And I hope that I've convinced you that there's a lot to do in pulsar science. There's a lot of rich modeling opportunities and observation opportunities. And with that, I thank you for your attention.
Great. Thank you so much, Christo. Fortunately, because we lost a speaker, we've got a little bit of extra time for questions. So are there any questions in the room? Yeah, David's got a question.
Very nice talk, Christo, and clearly you're doing lots of different interesting things. I just wanted to ask you, what are the prospects of observational gamma ray observations, TV gamma ray observations of some of these systems with CTA in the future? In particular, I'm thinking here of the transitional millisecond pulsars, spider binaries, those sort of objects.
Yeah, that's a good question. Thanks, David. We are pushing, at least for HAZE, to look at spider binaries already. We've written a number of observational proposals. We got some data, nothing staggering and outstanding yet, but I think we're close to the HAZE limit and sensitivity limit for this type of systems. But we really hope that we can break a barrier with CTA, which will be 10 times more sensitive. Then there's really a pulsar program being contemplated for CTA. And since we've seen with the various present-day Cherenkov telescopes, we've seen a handful of pulsars, 4 or so. We really hope that we'll see quite a few more. So at the moment, we're in that gap of doing the modeling and proposing things. And I'm very hopeful and excited about the prospects with CTA. And we will clinch a few more of these and learn more. So yeah, I think that is what I can say for now. And there's one in the chat. Let's see.
I'm just going to read out that question for everybody in the room. So this is from Lawrence Norris. Sorry for what might seem like an unschooled question, but are gamma ray emissions superimposed on radio emissions or on headers or footers on the other?
I'm not totally sure what you mean, but we see, let's answer this way. We see gamma ray and radio emission from the same object, and they are sometimes in phase, out of phase, usually out of phase. And we model this to these to try and constrain the physics in the pulsars. I don't know if I'm kind of getting to what you're saying or asking, but it's...
So Lawrence, if you, oh, he says yes, thanks. Okay.
Okay, it's from different instruments. So we just collate data from different instruments and model these as a single model, within a single model.
Okay, great. We have another question on Zoom from Brian. Brian, do you want to unmute and ask your question? I think.
Hi, thanks, Chris. Great talk. Yeah, I probably would have asked you over tea, but we can't do that now. So you skipped over the spider binaries, but there are sort of similar ideas in terms of the pulsar when creating shock fronts. With the modeling and stuff that you're doing in terms of the structures and the actual pulsars, I mean, we always sort of think of these as just a uniform outflow. Do you think that could have any effect on what we see in terms of, changes in the shock structure, depending on how close the shocks get to the pulsars, or could this have some sort of observable feature that we could look for with CTA or HAZE?
Yeah, so I think you're right. There are different types of modeling. What we do is invoke some kind of structure which is maybe mathematically simple and simplistic, and then look at the emission output and see if we can constrain the energetics and stuff like that. And also via the light curves, you can get an idea if your geometry is at least to 0th order correct or not. Is it wrapping around the pulsar, or is it wrapping around the companion? Things like that, that will move your maximum flux position and minimum flux position around in your eclipses and stuff like that. What you really would need is MHD type of modeling. Some people are looking at that, and there's a very recent paper by Cerrone and company on peak modeling of this type of phenomenon. So it's not as simple as we make it out to be. It's not a simplistic structure that we just use to get the model going. They actually see magnetic islands and reconnection and all kinds of funky stuff happening that I suppose we'll have to take into account for the next round of modeling. But definitely there's lots going on, and the more radiation or emission we can sample from these systems, the better we can constrain even the geometry of the shock and the implications that would have on the light curves and the acceleration and the spectra and so on.
Thanks.
Any more